Okay, let's start to implement particle swarm optimization in MATLAB. First of all, we need an optimization problem to solve using PSO. We choose a simple optimization problem. It's the minimization of the value of a function called a sphere. It is defined as f(sph) of x, where x is a vector in the Rn space. So x is a vector and the value of function for x equals to summation of xi squared. I is from 1 to n, or simply it's the norm of x squared. This is the sphere function. It's a very simple function, and we know if the search space is Rn, the global minimum of this function is the origin, where all components of x equal to 0. We would like to implement PSO to solve this problem. However, this is for educational purpose, and we intentionally choose this simple problem to make the implementation of cost function as simple as possible and focus on the implementation of PSO itself. Okay, let's go to MATLAB and implement the cost function and then implement the PSO step by step using MATLAB programming language. Here we create a new function using the edit command. Let's undock this from the main window and create a function which returns a value named z, and the name of function is a sphere and the input is x. The definition of function is the summation of all components squared. So z equals to summation of x element-wise squared, and this finishes the implementation of the sphere function. So now we have an optimization problem. Okay, let's save it with the name of a sphere and create another file. This file, let's save it with name PSO, contains the implementation of particle swarm optimization. Firstly, we will implement this as a script. Then we'll convert it to a function which can be used to solve any kind of optimization problem. Okay, let's start this program with CLC, which clears the screen, the main window of MATLAB, clear, which clears the workspace, and we make sure that there is not any unneeded variables defined in the workspace, and close all, which closes all figure windows maybe previously created by MATLAB, and this make sure that there is not any unnecessary figure windows opened in MATLAB. In general, implementation of metaheuristics can be done in several sections. These sections have logical meanings and enable us to make a logical process of implementing metaheuristics and make the code more readable. The first section is the problem definition. The next section is the parameters of the algorithm, parameters of PSO in this case. And the next section is the initialization section, which makes ready the algorithm to be started. And the next section is the iteration section and the main loop of algorithm, main loop of PSO. And the final section is the results section. These 5 sections contain all needed parts of the implementation of particle swarm optimization or any kind of metaheuristic. If you see our implementations of other metaheuristics shared on yarpes.com, you will see that all of them share these sections. Okay, let's start with the problem definition section. In this section, we are going to define the optimization problem which is being solved by PSO. The main component of the problem is the cost function in this case. It's an objective function that we'd like to minimize its value. So the cost function is defined as a function of x, which returns the sphere x. This helps us to refer to the cost function with a common phrase as cost function. And if in future we would like to change our cost function, for example, to a function named myCost, just the line 7 is modified and the other parts of the program remain unchanged. Okay, let's change the cost function to sphere and continue with the definition of search space. Let's comment out this line with cost function. The number of variables denoted by n_var. How many decision variables or unknown variables exist in this problem? For example, in this case, we are searching in a 5-dimensional search space. So x is a vector in R5, a 5-dimensional space. So the number of decision variables is denoted by n_var, and this is the number of unknown or decision variables. The vectors containing solutions are matrices at all. The size of these matrices or vectors is defined by a variable named var size. So any position, any solution in the search space is a vector of size 1 row and n_var columns. So our solutions are horizontal vectors, not vertical vectors. A horizontal vector with 1 row and 5 columns in this case. So this is the matrix size of decision variables. Using tab, we align these comments for the neatness of code. Let's define the range of variables. We defined the cost function, the number of variables, and the definition of range for the decision variables remains. The minimum value of variables, varmin. In this case, we assume that the -10 is the minimum value of the variables. So we comment this line by lower bound of decision variables. And just like the lower bound, we define an upper bound to +10 as the upper bound of decision variables. All of 5 decision variables are real numbers from -10 to 10. So our search space is the 5-time Cartesian product of this range from -10 to 10 to itself. We are searching for a value in this range which minimizes this function, which is defined as cost function using this function handle notation in MATLAB.